Good morning, ma'am. I am B. Suman from AC department. My roll number is 234G18049. Today's my topic is transmission line equations, derivations, and analysis. Introduction to transmission lines. Transmission lines are critical components in electrical engineering that transport electrical energy from one point to another. Understanding their behavior is essential for designing efficient communications and power systems. This presentation will cover the derivation analysis of transmission line equations. Definition of transmission lines. A transmission line is a specialized cable or wire that connects electrical components over a distance. They are characterized by their impedance, capacitance, and inductance per unit length. Transmission lines can be categorized into different types based on their frequency length relative to the wavelengths. The telegrapher's equations. The fundamental equations governing transmission lines are known as the telegrapher's equation. These equations relate voltage and current along the length of the line to its physical parameters. The telegrapher's equation can be written in both time domain and frequency domain forms. Derivation of telegrapher's equation. The telegrapher's equation are derived from Kirchhoff's voltage and current laws applied to differential lengths of transmission lines. By considering the voltage drop due to resistance and reactance, we can formulate these equations. The resulting equation describes how voltage and current vary along the line with respect to time and space. Parameters of transmission lines. The key parameters of the transmission line includes resistance, inductance, capacitance, and conductance. These parameters determine the performance and efficiency of the transmission. Understanding these parameters is crucial for analyzing signal integrity and power loss. Characteristic impedance. Characteristic impedance Z0 is a critical parameter that describes how voltage and current behave on the transmission line. It is defined as the ratio of voltage to current for a sinusoidal steady state signal. The characteristic impedance can be calculated using the formula Z0 is equal to square root of L by C for lossless lines. Wave propagation on transmission lines. Wave propagation is a fundamental concept in understanding how signals travel along transmission lines. The speed of wave propagation is influenced by the line's inductance and capacitance. This wave behaves leads to phenomena such as reflections, standing wave, and attenuation. Reflection coefficient. The reflection coefficient quantifies how much to the incident wave reflected at the junction or discontinuity. It is calculated based on the characteristic impedance and load impedance of the transmission line. And now understanding the reflection coefficient is essential for minimizing signal loss and distortion. It is calculated based on the characteristic impedance and load impedance of the transmission line. Losses in transmission lines. Transmission line experience various types of losses including resistivity loss, dielectric loss, and radiation losses. Techniques such as using low loose materials and optimizing line design can mitigate these losses. These losses can significantly affect the performance, especially over long distances. The techniques such as using loose materials and optimizing line design can mitigate these losses. Conclusion and application. Transmission line equations are fundamental for analyzing and designing communications and power systems. A thorough understanding of these equations enables engineers to optimize transmission line performance. Transmission line equations are fundamental for analyzing and designing communications and power systems. A through understanding of these equations enables engineers to optimize transmission line performance. Future advancement in transmission line techniques will continue to improve efficiency and reliability in various applications. Thank you, madam.